So let's start. So I am Harish. I am from ISER Mohali, and I will be conducting your uh, this live interaction sessions for Algebra 1 course on each Friday from 6 to 7. So we have already seen assignment 1, 2, and 3 of the last year's course, and now we are going to discuss assignment number 4. My screen is visible, right?
Yes, sir.
Okay, thank you, Shalini. So we will start by recalling some of the theorems that is required to solve this assignment. So the first is the first Silo theorem, which says that if G is a finite group and the order of G is P raised to D times M, where M is something which is co-prime with P. P does not divides M, you mean that P has to be co-prime with M. So and D and M are anything which is greater than equal to 1 and such that P does not divides M, which implies that P and M are co-prime, right? Uh, so then there exists a subgroup H of G with order of H equal to P raised to D. So in the order of G, the highest power of P is D, right? Because M is not divisible by your P. So what this theorem says that G has a subgroup whose order is equal to the highest power of P in uh, in the order of G, right? So this is first Silo theorem. I hope you all guys have seen this before. Second Silo theorem says if you take any two pre-Silo subgroups of a group G, then they are going to be conjugate to each other. Okay. The third one says with with the same assumptions as in theorem 2, if S denotes the number of distinct p-shallow subgroups of G, then that number is congruent to 1 modulo P. So what information you have over shallow p subgroups? First of all, theorem 1 says that shallow p subgroup exists. Second theorem says that what any two shallow subgroups are conjugate, and the third theorem says that their number is congruent to 1 mod P. That means P divides the number of P shallow subgroups minus 1. Okay. Now I have added one more theorem to these because that's also going to play a crucial role in whatever calculation we are going to do today. So it says the number of P shallow subgroups in G equals order of G divided by order of uh, normalizer of P, where P is any P shallow subgroup of G. In particular, we this theorem says that this number is a divisor of order of G. So that part is important, that for any P, the number of P shallow subgroups in G should be a divisor of order of G. Okay. If you want a proof of this statement, or if you want to know more about this statement, then I have taken this statement from the Ian Hustein's book, from the group theory chapter, and the section is on shallow subgroups. So there you will find this theorem as well, and it plays a crucial role in computation for whatever computation is related to p-shallow subgroups. So it's also useful in our uh, assignment today. So uh, first of all, I want you guys to be more focused on this assignment because these questions are really important, and the techniques that we are going to use in today's assignment are really important, and you may find similar kind of questions in your PhD entrance exams and your interviews, because you will come to know as soon as we proceed with the assignment that how beautiful the results are going to be. So the first question is, a simple group is a group in which there are no proper non-trivial subgroups. I hope you all know that. In a simple group of order 168, how many elements are there of order 7? Okay. It means that no non-trivial normal subgroups. Okay, so just a small correction here. In a simple group of order 168, how many elements are there of order 7? So you are given that the group has order 168, and you need to calculate the number of elements of order 7 in this group of order 168. So it's a very general result. You can see you are just given the order of the group and the fact that it's a simple group. You need to calculate that how many elements of order 7 it has. So explicit number, exact number you have to find. So these kind of questions you can find, as I already said, in any of your exams. So yeah, so any guesses how we can approach? The hint is we need to use whatever we have written, whatever I have written above. One of these theorems we have to use, maybe more than one, and maybe one theorem is used more than once also. So how can we start?
Sir, we can use Silo third theorem.
Yes, and how you are going to use that?
We can find number of 7 SSG
Okay, okay,
in this, then
okay.
count the element of order 7 in that 7 SSG. Yeah.
Yeah, yeah, you're right. So yes, so let's start doing that. You're right, Shalini. We are going to use the same trick. So there exists a shallow subgroup of order 7 because you can directly see the prime factorization of 168 is 2 cube times 3 times 7, right? So mm, by first shallow theorem, we can say that there exists a 7 shallow subgroup of G, right? Because 7 is a divisor of uh, this 168 and the highest power is 168, so there will be even subgroups of order 7. Okay, now so I will be using the same notation as given in the lecture notes. So let n7 denotes the number of 7 shallow subgroups of G. Okay, so what information we have been given on n7? So by you can say the third shallow theorem. So what does this says? N7 has to be congruent to 1 mod
Mod 7.
7. Yes, exactly. So what is the possibility for N7? N7 can be 1, 8, 15, and so on. But we have one more uh, property on number of shallow subgroups. Theorem 4 says that this number is a divisor of order of G. Okay. So now we will use this theorem. I'm just writing here theorem 4 and 7 must divide order of G, which is 168. Okay, this also gives you one more thing. If n7 is congruent to 1 mod 7, so is can n7 divides 7? No, right?
No,
Because it's congruent to 1 mod 7, right? So it implies that n7 does not divides 7, or in general np does not divides p, right? So uh, how we can use that? So 168 is 2q dot 3 dot 7. So n7 does not divide 7. So what does this means? This This implies n7 has to divide whatever is remaining,
24.
24, right? So what are the possibilities for n7? See, 1, 8, 15, and then you have 24. After that, everything will be larger than 20, 1, 8, 15, and 22. Then you have 29. Okay, then everything is greater than 24. And out of these numbers, what are the divisors of 24?
1, 8.
That's it, right? 1 and 8. So, still we are left with two choices. So, let's first see what happens if n7 is 1. If n7 is 1, then uh, let P be the unique 7 silo subgroup of G. And do you guys know that if the silo subgroup is unique, then it has to be normal?
Yes, sir.
How we can say that?
By using second Silo theorem, all all Silo PSSG are conjugate to each other. If it is 1, then all the conjugate equals to the P, so they are normal.
Yes. So the reasoning is, for all G belongs to G, your GP inverse is of silo sub. First of all, it's going to be 7 silo subgroup, because it also has the same order, right? Conjugate of a subgroup is also having the same order. And by theorem 2, or I should say the second silo theorem, second silo theorem, all 7 subgroup are of the form GPG inverse. So what I'm saying, for any G, GP inverse is a 7 silo subgroup, and all 7 silo subgroups are of the form GPG inverse. So the set of 7 silo subgroup is just the conjugates of G, right? And just add a page here. So what does this imply? All shallow subgroups are just conjugates of P, but since N7 is 1, what does this mean? That GPG inverse is equal to P, because you have only you have unique shallow 7 shallow subgroups. All conjugate has to be equal to G. So GPG inverse equal to P for all G belongs to G, and that implies that P is normal in
Normal.
G. But this is a contradiction. Why? Because we
Yes.
assume that G is simple, right? So this simply implies that N7 has to be 8. Number of 7 silo subgroups is 8. Now from here we need to calculate the number of elements of order 7. So you can see that each 7 silo subgroup is of order, highest power of p here is just p, is of order 7,
7.
and hence it is going to be cyclic. It is cyclic and has, and thus has 7 minus 1, that is 6 elements of order
7.
7. So total number of elements of order 7 in G is,
48. 8 into 6.
yes, good Shalini. Others can also speak. Uh, no matters whether your answer is correct or wrong, at least you should be there in the interaction. That way you will learn more, I guess. Total number of elements, okay, of order 7 is equal to 6 into 8, that is 48. Okay, so 48 was an option there. Okay, so it's going to be the correct one. Okay then. So is everything clear to everyone? If someone has any doubt, then you can ask, or otherwise we will move to the next question. So your silence says either you are getting everything or you are not getting anything.
Clear, sir.
Okay, Shalini, it's clear to you. What about others? See, interaction only is helpful to you guys, not for me. I will do whatever uh, I'm supposed to do, but it's beneficial for you if you are interacting. Okay, then. So second question is true or false. Every finite group of order 72 is not a simple group. That question is also tricky, and we will use the Silo theorems, but in a slightly different manner. So at least the first part is very much similar in these kind of questions. First of all, we need to uh, see the prime decomposition of it. So it's 72 is 2 raised to 3 and 3 raised to 2, right? 8 into 9. Now, either you can go with silo 2 subgroups or silo 3 subgroups. You can try both, but I tried to solve this question with silo 3 subgroups, and I got success. So I'm just doing that. You can try the same, whether the same argument works if you or not if you start with silo 3, silo 2 subgroups. Okay. So this, as there is a factor of 3, so it says that there is a by first theorem there is a silo 3 subgroup for sure. Now number of silo 3 subgroup, we are denoting it with n3. So n3 congruent to 1 mod 3, and I'm not rewriting which through which theorem it follows. I hope it's clear to everyone till now. And n3 divides the order of G, right? But order of G is this, and n3 is co-prime with 3, right? So this implies n3 congruent to 1 mod 3, and n3 divides 2q, which is 8. Because n3 is already co-prime with 3. You can see that uh, n3 congruent to 1 modulo 3. So n3 has to be a divisor of 8, and it has to be something which is congruent to 1 mod 3. So what are the options from here? It says
1
n3
and 4.
yes, n3 is equal to 1 or 4, right? So again, someone has this. Okay. So here we go. So N3 is either 1 or 4. In both condition, we have to prove, see first of all whether it's simple or not. It's a true false question. So it might be simple or might not be simple. So we'll check one by one what happens when N3 is 1 or N3 is 4. See, N3 equal to 1 is a simple case, right? We already saw that if the silo subgroup is unique, then that subgroup is normal, right? If N3 equal to 1, then what we can say, uh,
Then G is not simple.
that G is not simple, right? Then uh, we have three silo subgroup is I'm starting three silo subgroup is unique, and that implies, let's say if the three silo subgroup is denoted by P, it's unique, and as P is normal in G, which implies G is not simple. So this case is handled very easily. Now, what if N3 is 4? This is a bit tricky case. See, if N3 is 4, then uh, we have 4 3 silo subgroups, right? And they are just conjugate of each other. Uh, and by theorem 2, they are of the form P G P, say G1 P G1 inverse bit of G, I think I can use GP G inverse H P H inverse and say K P K inverse for some shallow subgroup P of G and G H K are the elements of G. Okay, so we can take the four three shallow subgroups to be of this form. We all agree because they are going to be conjugate of
Yes,
each other,
sir.
right? So you can just fix one and the other one is and name it as P, and the others are going to be conjugate of each of that P. So you can take them to be of the form GP, G inverse, and so on. So now let's say this S is the set of all three silo subgroups. Okay. So mm, can you see a natural action of the group G over this set S? G acting on
Uh,
S.
by conjugation.
Yes, you're right, Shalini. So by conjugation, G acts on S by conjugation. For those who have not attended the previous lecture, so action by conjugation is simply this. An element of G, I should write a different element, because G I am already using. Let's say small l comma a subgroup, an element of S. Let's say small s. It's been mapped to L.
S.
Yeah,
uh,
it's just notations, because at least we should use something which is capital S to denote the group or subgroup.
yes, sir.
So L, N, and then L inverse. Okay. So this is a group action you can check, because whatever element you pick, you conjugate it again, you are getting an element of this set, and it satisfies the properties of group action as well. So it's a group action. So this is a group action. I see what this group action is doing actually. It's permuting the elements of S, right? If you pick an element of S, you act an element of G, it will give you something else. Okay. So this conjugation is permuting the elements of S, right? So this action induces a homomorphism of this. I should say this action induces the following homomorphism. So what is the homomorphism?
Uh,
In
from G to permutation of S.
S4, we can say. Okay, the four symbols are just uh, your P.
S4.
uh, so it's a, because each element of G is acting through a permutation, or as a permutation you can say. Okay, or if I want elaborate a bit this, then I can just say that say this is your homomorphism. Say this phi. Phi is a homomorphism. So what phi of G belongs to S4, right? So what phi of G does? Phi of G somehow permutes an element of S. So phi of G n, what does it, what it does? It just send n to Gn G inverse. Okay, where n you already know is one of these. Okay, so and this conjugation is like a permutation for a fixed G. This conjugation is like a permutation, right? Because that
Yes,
fixed
sir.
G can send this P to anything which is inside this set, or this element also anything which is inside this set. So it's acting like a permutation. So, on four symbols, and your symbols are just these four, the four subgroups, the four shallow subgroups. Okay. Now this induces a homomorphism phi of G. So what we can say about this homomorphism? This homomorphism is going to be used again in the next question. So just be more focused. So can kernel of phi be just identity? Can we have this kernel to be identity? Can this map be injective? Any guesses? Yes, no?
No, sir.
Okay. We have one answer is no. Anyone else supporting yes or supporting Shalini? No one, all others are independent candidates, right? Okay, then any response? Yes, no. If you're shy to write to interact, then you can also write in the chat. Okay, so yeah, it cannot be identity. Shalini, do you have an argument for that? Why it can't be identity?
No, sir. Just applying the definition of kernel. Uh, that in
Hmm.
kernel we have element of the form such that phi of some g equals to identity of this like this. But I am not clear, sir.
Okay, so I don't know how you are going to apply it. I think it's going to be a bit cumbersome. But a simple way to see this is, see, what is your order of G? 72, right? What is order of S4? 4 factorial, which is 24.
24.
Can there exist an injective map from G to S4?
No, I have not noticed the order.
Yes, because see, order, if something injective map exists, then order of S4 has to be greater than order of G, right?
Yes, sir. Yes,
Therefore,
yes.
there does not exist an injective map. Whatever you are trying to do is okay, but I think that that would be more problematic. You need to
Yes,
add so
sir.
many
Yes,
steps,
yes.
and
Yes.
so there does not exist an injective map from G to S4. Okay. Now I will take you guys to the other extreme. Can kernel of phi be G? One extreme is not possible. What about the other? I think it's too much for you to think at at this moment. So I will do it of my own. So see, if kernel of phi is G, what does this mean? Then this homomorphism from G to S4 is a trivial homomorphism. It's mapping everything to identity.
Yes, sir.
Okay, is a trivial homomorphism, but that cannot happen. Why? Because uh, and this implies phi of G is equal to the identity permutation for all G in G. So whatever G you are taking, as it's a trivial homomorphism, this will implies that the action of G on S is trivial. Means each element of G is fixing uh, each element of S. And what does this means? That G and G inverse. That's how we were acting this, right? Or if you want to write it in terms of homomorphism, then phi G of N is what? Phi G is identity for each G. So it's just identity N, it's N.
N.
And what is by definition? It is Gn. G inverse, and that's happening for all G in G and for all N in S. So what does this mean? This means that G and G inverse is equal to N for all G in G and N in S. But can it happen? So that will imply that each element of S is a normal subgroup.
Yes, sir.
Okay, and thus by definition of S, what kind of elements you have in S? They are just conjugate to each other.
Yes.
Thus, by definition of S, we have cardinality of S to be just one because all are normal and they are just conjugate to each other. So if something is normal, its conjugate has to be the same again. Okay. So if you pick any element of S, it's a normal subgroup, and the remaining three are conjugate to the first one by the definition of S. So it's normal. So all of its conjugate has to be the same. So what does this mean? That S has the single element, but that's a uh, clear contradiction to the cardinality of S, right? Because we assume that the order of S is 4. The number of shallow subgroup is 4, right? So we got a contradiction. Thus, what our assumption is not correct, and that means the kernel of phi cannot be G. Okay. So combining both of these facts, we can say that kernel of phi is a proper,
Proper normal
yes,
subgroup.
non-trivial
Normal subgroup.
normal subgroup of
G.
G. And what does this mean? G is not
Simple.
simple. Okay. So in both the cases, when n4 n3 was 1 and when n3 was 4, we got the same result, that the group is not simple. So what is the answer? Every finite group of order 72 is not a simple group. It's going to be true, right? Okay. So if anyone has any doubt, then you can ask me. Otherwise, we will move to the next question. Okay. So the same trick has to be used again to solve question number 3. It says that there exists a simple group of order 24 and there exists a simple group of order 36. Then there are options that whether A is true, B is true, and both are true, both false. Whatever four combination you can have, it's there. So we just need to check that which statement is true and which statement is false. There is nothing different in this question as well. We are going to use the same trick again as we used in question number 2. So if uh, for 24, let's say there is a simple group of order, we are checking for 24, let order of G is equal to 24. What is 24? It's just 2 raised 3 times 3. So again, we can proceed similarly to uh, through same as question number 1. So using the same idea as of uh, question 2, we at least get that if n3 is equal to 1, then G is not simple. See, we have 72 earlier, right? Which is the 3
Yes,
times
sir.
3 times 24. So you have one more power there of 3, but that's not playing any role in computation.
Yes, sir.
N3 is again going to be 1 and 4. If it is 1, then
Yes.
it's not simple. Okay. And if N3 is 4, then the same map you can define again. I'm just writing it as Q differently so that you guys are not confused with 5. So if N3 equal to 4, then we can define the homomorphism from G to S4. And by the same reasoning, kernel of phi is not equal to G. The only trick here is what if the kernel of phi is identity. Here the order is 24, which is the order of S4. Can kernel phi equal to identity? So our earlier argument won't work. Still, can we say something? See, if kernel of phi is identity, then you guys agree G is isomorphic to S4 because
Yes, sir.
phi is a homomorphism, phi is 1 1, and they both have the same cardinality. So 1 1 implies onto if the set says same cardinality, right? So phi
Yes,
is a
sir.
so G is same as your S4, but Sn are not simple for n greater than equal to 3.
Yes, sir.
Which normal subgroup it has?
AN,
Yes,
alternative group.
yes, yes. And as A4 is a normal subgroup of S4, so S4 is not simple. Thus, G is not simple in this case. So this case might occur, but even if it occurs, then the group is going to be a non-simple group. And if kernel phi is a non-trivial proper subgroup of G, then we have it in the trivial way, right? Similarly, basically kernel phi is always normal in G and it's non-trivial proper also. So that will imply G is not simple again.
Simple.
Okay. So at least the first statement is not true, which says that there exists a simple group of order 24. There won't exist because all groups of order 24 are going to be not simple groups. So there won't exist a group of order 24 which is simple. So now let's move to this other part, B part, which says that there are just a simple group of order 36. So there won't be any difficulty here because here the size is already 36, which is greater than 24. So you can proceed in the same manner you have done for order of G to be uh, 72. Okay.
Yes, sir.
Okay, let order of G is 36. So I'm not repeating the same arguments again. I'm just writing proceed same as question number 2. So both of them are in both the cases. Why I'm saying this, because 36 is what? This is 4 times 9.
9.
So here you just have uh, one less power of 2, but you still have the both the options, and 3 can be one of
Sir, 3
4.
square.
Oh, yes, yes, yes. Yes, thank you, Shalini. So still you have the same options for N3, right?
Yes, sir.
Because there we have N3 to be a divisor of 8, and then we were getting the possibilities to be 1 and 4. Uh, yes. N3. So if we take N3 divides 2 square, then it's going to be 4. And then also we have the same possibilities, and N3 is 1 and 4, and then you have to proceed in the same manner. So this 2 uh, less power of 2 doesn't uh, make a difference. If it would have been 2, just 2, then it would have created a difference. It would have been a much simpler case. But if it's 2 square instead of 2 cube, then there is nothing going to be changed. You can proceed in the same manner. Okay. So in both the cases, we won't get a simple group. Okay. I hope it's clear. Someone has written in the chat. Okay. Okay. So let G be a non-abelian group of order PQ such that P and Q are distinct primes satisfying Q congruent to 1 modulo P. Consider the following statement. So before going to the statements, can we say something about the order of how this ordering is happening between Q and P? So, see, this implies P divides Q minus 1. Okay.
Yes, sir.
And this implies that P has to be smaller than Q, because if P equal to Q, then definitely this won't happen, that P divides P minus 1. And if the other way is around, if Q is smaller than P, then Q minus 1 has to be smaller than P, right? Then in that case also P cannot divide Q minus 1. So this directly says that P is the smaller prime and Q is the larger prime. Okay. So the relation we got straightforward. Now the question says there are P silo subgroups, P silo Q subgroups. So it's just confusing statement. It says the number of silo Q subgroups is P, and the B statement says the number of silo P subgroup is Q. Okay, so
Yes, sir.
we need to check that which of these statement is correct. So let's proceed. The same trick we will use again. We will first work with NP and then with NQ. Nothing changed. Let's start with uh, what you want. NQ case is easier. So let's start with NQ, I guess. So we have NQ congruent to 1 mod P, and NQ must divides order of G. But order of G is,
Sir, 1 mod Q.
oh, yes, yes, yes. Thank you, Shalini. Uh, yes. So NQ is also a divisor of order of G, which is PQ, but NQ and Q are co-primes. So this just implies that NQ is a divisor of P. But what are the possibilities for a prime, uh, for a divisor dividing a prime number?
1 and P only.
Yes. So NQ is just 1 or P. And from here we have NQ to be 1 or something like, you can say Q plus 1, because Q plus 1 is also 1 times uh, 1 modulo Q, or 2Q plus 1, and so on. So first of all, both these conditions gives you at least one thing. These both implies that NQ can be 1, right?
Yes, sir.
Okay. And I will say that NQ cannot be P. Can anyone give me the justification why? Everything is there on the screen.
Sir, if NQ equals to P, it means P is congruent to 1 mod Q. It means
Yes,
Q divide P minus 1, which is not possible as P is
yes,
less than Q.
yes, yes, yes. Good, Shalini. So this simply implies uh, NQ congruent to, sorry, P congruent to, if you are choosing NQ to be 1, P congruent to 1 mod Q, and which implies Q divides P minus 1, which is a contradiction to P is less than Q, because P minus 1 is would be less than Q, so Q cannot divide P minus 1. So you just have one possibility that at that NQ has to be 1.
1.
Okay. So the statement saying that there are P silo subgroups, uh, sorry, there are P many silo Q subgroup, this statement is clearly false. The number of silo Q subgroups is just 1. Okay. Now the second part, what we can say about silo P subgroups. So before that, let me write something else, so that would be required later. Mm, Let's give some name to this P silo subgroup. Let, sorry, Q silo subgroup. It's unique, so I should write let the Q silo subgroup of GB Q. Okay, I'm just noting it with Q. Okay, that is okay. So NP is, let's start the calculation for NP. NP is 1 mod P, and NP must divides the order of P, which is just PQ, and this says NP must divides Q, right? Because
Yes,
NP is
sir.
co-prime to P. And what are the possibilities from here?
1 and Q.
1 and Q. First of all, let's write the possibilities in terms of 1, 1, P plus 1, T, 2T plus 1, and so. But we have already seen that Q is congruent to 1 more P. It's Q, right? Q is congruent to 1 more P. So P Q will satisfy this and one will also satisfy. So here now NP to be 1 or Q. In addition to that, you are given, since Q congruent to 1 mod P, this you are already given. Therefore, both the possibilities of NP survives from these facts. So NP is 1 or Q. Okay. From
Yes,
here we are
sir.
getting 1 or Q, and here also 1 is congruent to 1 mod P and Q is congruent to 1 mod P. So both the conditions is okay till now. We need to check separately which condition is creating a problem. So let's start with NP to be 1. If NP is 1, then the P shallow subgroup is normal. That we have already seen. Why? Because it's going to be unique and all conjugates are going to be same again, so it's going to be normal. And let that let the now it's unique, so I can use that the the let the p shallow subgroup be p, because there is unique, so I can denote it with some symbol. So your the unique q shallow subgroup was capital Q, and the unique p shallow subgroup is capital P. Okay. And in addition to that, your P intersection Q is empty. Why? Because order of P and order of Q are co-prime. If something, if this P intersection Q is non-empty, then it has some order that has to be a divisor of order of P and order of Q. So there is no possibility for it except one. So it has to be identity. So you have uh, with addition to that, you also have order of P times order of Q to be order of G. So you have two subgroups which are normal and which are uh, with P is normal in G, Q is normal in G. Their intersection is trivial. Their product of their order is equal to G. This implies that G is just
Direct product of P and Q.
P and Q. Okay. So mm, this has order P, right? P shallow subgroup is of order P here because the group has order PQ and it has order
Q.
Q. So both of these groups are cyclic.
Cyclic.
This is cyclic and this is also cyclic, which implies G is abelian. But we assume that G is non-abelian, right?
Non-abelian.
So it's a contradiction to the non-abelian property of G, which leads to a contradiction. Okay. So number of p shallow subgroups, and the contradiction arises because we assume NP to be 1.
Yes, sir.
So this implies NP cannot be equal to 1, and or this implies NP equal to Q, because you just have two possibilities, 1 and Q. 1 is not there, so NP has to be Q. The second statement is correct, that the number of p shallow subgroup is Q. Okay, so first one is wrong and the second one is correct. Okay, if there is any doubt, then please ask. Otherwise, I will move to the next question.
Clear, sir.
Okay, thank you. Anushya, is it you, right? Okay, so definition for you guys, a perfect number. So a perfect number is a number which equals the sum of its divisors. For example, 6. In 6 you have three divisors, 1, 2 and 3. If you add them, you are going to get 6 again. In 28 also, the divisors are 1, 2, 7, 14, 1, 2, 4, 7, 14 and 28. If you add them, you will get 28 again. And same in 496 you can check. So these are perfect numbers. So a perfect number is one in which the sum of divisors is equal to the number again. Okay. So you can search more about it on Wikipedia that you already know. So here's a problem. A group whose order is an even perfect number is simple. So before solving that, I need I want you to know this fact. This is not given in the question. So even perfect number has a specific form, mm, and that is all even, not all even numbers, all even perfect numbers are of the form. They have a specific form, and that form is 2 raised to p minus 1 times 2p minus 1, where p is a prime and this coefficient, this product, this term in the product 2p minus 1, it's also a prime. So p is a prime and 2p minus 1 is also a prime number. So we are given that order of g is equal to 2p minus 1 times 2p minus 1. Okay, where p is a prime and this number is also a prime. This number is prime. So how many prime divisors you can see for order of g? This is simple. Yeah, this you all should be able to answer. You are given a odd prime factorization of order g. What are the primes that are dividing order of g?
2, 2 raised to the power
Yes.
p minus 1.
Is it a prime? I'm saying what primes divides 2p minus 1. Except Salini, anyone else want to say something? At least one I have already written. It's too bad.
2 raised to the power p minus 1.
Yes, 2 raised to power p minus 1. Okay, so you were saying the same thing before, or 2p minus 1. Okay, so it's a prime, and one more prime is na 2 is also a prime, which is dividing order of g.
Yes, sir.
So there are two prime divisors for order of g, and I will say, uh, let's try with the new candidate we are getting here, because see, this perfect number has some specialty. It has a prime of this form, and this order of g is this form. So what you expect that which prime will play a crucial role? This prime, right? 2p minus 1. So let's start with this and see what we can say about the number of shallow subgroups of it. So n 2p minus 1, it is congruent to 1 modulo oh,
2p minus 1.
yes, thank you Shalini, at least you are awake. So and NP must divides order of G. So it is co-prime with 2p minus 1 and oh sorry, not NP, it's has to be replaced by whatever the prime is. So our prime here is 2 raised to p minus 1. Okay, so it must divides order of G, so which is already written there. So it is called n n 2p minus 1 is co-prime with 2p minus 1. So whatever remaining 2 raised to p minus 1. So it simply means n 2p minus 1 has to divide 2 raised to p minus 1. And from here what you can get, n 2p minus 1 is equal to 1, or 2p itself, 2p is there, and so on. Because 2p is also 1 congruent to 2p minus 1, right? After 1 you will get this choice only. So then anything else is bigger than 2p. So what does this says? So this number has to divide 2 raised to p minus 1, and this number is of this form, is either 1 2p or something bigger than 2p. So these two implies that np has to be
1.
1, right? Oh sorry, not np, I'm writing the same notation. It's n 2p minus 1, that is going to be 1, which implies the 2p minus 1 silo subgroup is normal in G, and that implies G is not simple. So if the order of G is a even perfect number, then G cannot be simple. So if order of G is 6, then it cannot be simple. If order of G is 28, then it cannot be simple. If order of G is 496, then it cannot be simple. It cannot be simple, and whatever perfect number you can find after 496, it could not going to be simple for any of them. Oh, we are lagging behind so much. Three more questions are pending, but they are not so difficult. They are going to be easy ones. So now it says let G be a finite group and P a prime such that P divides order of G. Then there exists a P subgroup of G that is not contained in any silo P subgroups. First, understand the statement. Look at it for once. So it says that there exists a P subgroup. P subgroup means a subgroup whose order is of the form P raised to something. So P subgroup is nothing. P subgroup is a subgroup which has order P raised to R, let's say, for some R belongs to N. Okay, so it's the statement is if you are having a finite group, P is a prime that is dividing order of G, then there exists a P subgroup of G that is not contained in any silo P subgroup. Okay, so I'm saying that the statement is false. So what we will prove that each P subgroup of G is contained in some silo P subgroup. Okay, so that we will.
Sir,
Yes.
sir, the screen is not completely visible. The
Now it's okay. You're not able to see the question.
I can't see the question completely. I mean,
Okay,
the
okay, okay. Okay, Ravi Shankar, thanks. So uh, it says uh, there exists a P subgroup of G that is not contained in any shallow P subgroup. So I'm saying the statement we are going to prove is this, that each P subgroup of G is contained in some shallow P subgroups. So the statement is false. There won't be such a P subgroup. For each P subgroup, you will surely find some shallow P subgroup such that that subgroup is contained in the shallow P subgroup. Okay, so let's see how we can prove this. This question is tricky. 7 and 8 are easy, so they won't take much time. This question will take a bit of time. So let's start with a let's start with a P subgroup. Attach be a P subgroup, and for and I'm taking T to be the set of all silo P subgroups. P is a subgroup of G such that P is a P shallow subgroup. Okay, then what? Uh, I'm going to use somehow the group action. So H is acting on T. We are having a subset, we are having a set which contains P shallow subgroups. The obvious action is by conjugation. H and some element of, now I can denote it by P because I'm taking general element to be P. It will be mapped to H, either H inverse PH or HPH inverse, whatever way you want to show the write the conjugation. So it's by conjugation. So yes, one thing you might have already seen, and size of orbit of any element of the set, what is the set here? T, right? This should divide the group acting on it, must divide order of H, right? Because H is acting on it, and H is a P group. So what is the possibility for it? This implies size of orbit of, we act like math student, we use symbols. Orbit of small orbit of P is some power of P, right? For all, and this is for some r greater than equal to 0, because it can be 1 also, na? Orbit of P can be 1, and if it is not 1, then it's just some power of P, because order of H is just some power of P, because H is a P group, and that's true for all uh, capital P inside T, right? Now if uh, let's split it into two cases. So just I'm using a different color, uh, distinguish. So if orbit of P is uh, greater than 1 for all P belongs to T, then what happens? Uh, when we have orbit of P, again P raised to R,
Some P raised to power R.
now we can choose R greater than 0, right? Or greater than equal to 1 simply. That's for all P in T. But what does this implies? This implies that P divides the order of orbit of P for all capital P inside T, right? Because now it's greater than equal to 1, so at least it has to be P. So P divides order of the orbit of P for all P inside T. But okay, and since the group is acting on T, so T can be decomposed as orbits, right? Orbit of P where this union is over distinct. We're taking this union over uh, disjoint orbits, we can say. It can be written as a union of its orbit, right?
Disjoint orbits. Yes, sir.
Yes. So it is this disjoint orbit. This union is running, and what does this mean? This will simply imply this order of T is the sum of orbit of T, which is again disjoint running over disjoint orbits. Each orbit was divisible by prime P, so their sum is also divisible by prime P, and this will implies that P divides order of T, right? But uh, by the definition of T, what was T? T was the set containing all Silo P subgroups. So by third theorem of Silo, number of Silo P subgroup is,
Congruent to one mode P.
yes, by the definition of T, mod T has to be congruent to one mod P. So it's a clear contradiction, right? We are getting P divides order of G, and from Silo theorem we are getting T order of T to be one congruent to mod P. So it's a clear contradiction. And why we are getting the contradiction? Because we assume that each orbit has size greater than 1. So what is the conclusion? So this implies there exists some P inside T such that orbit of that P is the size of orbit of that P
Is
is 1.
one.
Okay. And what does this means? What action we were having? This implies uh, H was acting on the capital H was acting on T, right? Through conjugation,
Yes, sir.
and its orbit is 1. So each conjugating element is just fixing it. This implies, just to distinguish it from our usual notation, I'm writing it something else. Because now this P is specific. So what notation? Maybe P bar, P delta. Okay. So this will implies that H inverse P delta, H is again P delta for all H in H, and that means that your P delta commutes with each element of H, and which means your HP is same as your pH, right? So this is happening for all H in H. Okay. So if H and P are two subgroups such that HP equal to pH, this implies that pH is a subgroup of
Subgroup of G.
G. Yes. And P was a okay. P was a silo P subgroup, and H is just a P subgroup. So what we get, PH is a P subgroup of G, right? Because both have orders as some powers of P only. So their product will also have some uh, order of pH is just order of P times order of H, right? And order of P is a power of P, and order of H is also some power of this prime P. So their product will again have some power of P. So it's a P subgroup of G. Now, if H is not contained inside pH, then what will happen? Order of this pH would be strictly uh,
Greater than H.
yes, would be strictly greater than H. Misunderstood. Okay. Or you say, and order of pH is also going to be greater than order of P, right? Because if H is not contained inside, uh, I just made a small mistake. H is not contained in P, then order of pH has to be greater than, this would be the correct statement. Because if H is not contained inside P, then pH cannot be equal to P, right? P is already a subset of pH. You agree? Because this is
Yes,
all,
sir.
this is always true, na? P has to be a subgroup of pH. Now, if it has order strictly, uh, if H is not inside this P, then you are having some different elements, and those extra elements will force that order of pH has to be greater than order of P, strictly greater than order of P. Is it clear to everyone, or someone has any doubt? See, P is always a subgroup of pH, right? And if H is not inside P, then pH has to be uh, pH has must contain something extra than P,
Yes,
right?
sir.
So order of pH is greater than order of P, but this is a contradiction to the fact that P is a silo P subgroup, because being a silo P subgroup, it must be a group of order having highest power of P. But pH is a group which has some power of P as its order, and its order is greater than the order of this capital P. So this can't happen because P is a silo P subgroup. So, some other subgroup whose order is greater than P cannot have order as being some power of P. Okay. So you got the contradiction, and we got this contradiction because we assume that H is not contained inside P. This will imply that H is contained inside P. So that we were supposed to prove. So what we did, we started with a uh, P subgroup, and then we proved that there exists some silo P subgroup such that H is contained inside that silo P subgroup. In fact, we gave the explicit construction of that uh, silo subgroup. A small notational mistake I have made. So we were using P delta for this specific subgroup, right? The subgroup
Yes, sir.
whose orbit is P delta. So I can't use P here. So everywhere here should be P delta. P delta, P delta, P delta. So that's it. So P, what subgroup is? If you act H on T, which is a set of all silo subgroups, silo P subgroups, then the subgroup which has orbit whose orbit has size 1, that subgroup, that silo p subgroup will contain your H. Okay. So we in fact define, constructed or explicitly defined what is that silo p subgroup. Okay. So we can move to the next question. Next question says if G and okay, so it's just a definition of the commutator of GH. So you all are familiar with it. Derived subgroup, I think you all are familiar. It's just a subgroup generated by these commutators. The question says whether it's true or false that G is a finite P group for prime P of order Pn, where n is greater than equal to 2, then you always have commutator subgroup to be equal to G. So the question starts from here. If G is a finite P group for some prime P and order Pn, then commutator subgroup has to be equal to G. Forget about this hint. Without this hint also you can solve this question very easily. So I can just give you a better hint that the answer is false. Okay. Now can you give me an example where this doesn't hold true? A subfinite P group where the order of the group is greater than equal to P square. Okay. And commutator subgroup is not equal to G. What is the first group you know of order? Mm, it should be order 4 also will work, na?
Yes, sir.
G is a, G is a
Fourth
finite
order.
P group for 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 a prime P of order Pn. So if we take just P square, then whether for P square this commutator subgroup is equal to G. All
No.
subgroup, all abelian. These groups are abelian, na? Always
Yes,
abelian.
sir. Yes, sir.
So simple
Billion
counter
होएगा.
example is all groups of order P square are,
Or a billion.
are abelian, and thus GP GG is not equal to J. So
Equals to.
so this is false, right? Oh,
Yes, sir.
not equal to G, not equal to G. In this case, you have this is going to be identity,
Identity.
and thus GG is not equal to G. So what if I add some more fun to it? Uh, can is there an is there a non-abelian group which can be a counter example? So what is the obvious example you must think? First of all, you need to think over a group of order PQ, right? For being non-abelian, you need at least that order P and order P square you can't take.
Yes, sir.
So what is the first group you know of order PQ?
Q8.
Yes, Q8. Something else of order 8.
D4.
Yes. So D4 or Q8. So because in some books D4 is also represented as D8. So I'm just writing here D2 into 4. Okay. So it's of the form D2n. And you can also pick Q8. You can check for both of these groups, the size of the commutator is just 2. Okay. And in general, if G is a P group That's beyond the scope of this question, but I'm just writing it so that if you are interested, you learn something more. So if G is a P group, then mm, commutator subgroup of G is a subgroup of phi of G. I will say what is this phi of G, and it is strictly a subgroup of G. This phi of G is known as something called fraternity subgroup of G. You can Google it, what it is. By definition, it is just the intersection of maximal subgroups of G, and if there does not exist a maximal subgroup, which might be a case if you are in infinite setup, then it's just defined to be G. But if you are in a finite setup, then there will be some maximal subgroup, and that will force that its intersection of its intersection has to be a proper subgroup of G. Section of, because maximal subgroups by definition we take something to be of uh, first of all has to be proper. So intersection of maximal subgroups of G has again is again a proper subgroup of G. So, and why this GG is a subgroup of phi G, you can check that in for P groups we have this GG phi of G is just G, the group product of GP times the commutator, where GP is a subgroup generated by all pth powers. So this is some relation. So by this, the commutator subgroup is a subgroup of phi G, and phi G has to be the proper subgroup if it's a finite P group. Okay. So,
Yes, sir.
so this is in general true for any P group. G is a, you can Google it, or whatever example of P groups you know, you can try to check it for them. So that's why this won't be true. Okay. Now the smallest question of the day, at least in the number of words. So find the number of scalar two subgroups of S4. So using the same ideas, you can see this S4 has order 24, so it's just 8 into 3. Okay, you can see that using all these ideas, you end up with saying number of N2 is either 1 or 3. N2 has to be divisor of 3, right? So it is just 1 or 3. I'm not even using the other part, the modulo part I'm not using. So it has to be 1 or 3, and I can tell you the three silo 2 subgroups. So the N2 will be 3 only. Okay, so I'm just writing the 3 silo subgroups. So it's first one is identity, first element is identity, second is 1 2 3 4, and then you have 1 2 3 4, and 1 4 2 3, and then 1 3 2 4. It should have order 8, right? It's a silo subgroup, so it should have order 8, highest power. 1 3 2 4, and 1 4 2 3. So one is this, one is this, whether you have 1 2, then 1 3 2 4. These three elements are same. चीटिंग करने के चक्कर में लेट हो गए. So just copy and paste it. Oh, oh, oh. Is the screen visible? I somehow lost it.
No, sir.
It just got closed. Let me reopen it. I think the data might have been lost, so I have to write each and everything again. But I will do it and send you the notes. But let's finish this 8 question first. It's just opening. Somehow this application crashed. Oh, that's good. I can restore it. So yeah. Oh, okay. So whatever I write is there. Good. So where were we? With just solving the 8 question. Okay. So instead of being over smart, now I should write it. So 1, 2, 3, 4. These three elements are same. 1, 4, 2, 3, and 1, 3, 2, 4. The last these two elements will change. It will be 1, 2, 3, 4, and 1, 4, 3, 2. I can give you another subgroup H3 where you have identity 1, 4, 2, 3. Then again this next three elements are same 1, 3, 2, 4, and the last two are different. It's 1, 2, 4, 3, 1, 3, 4, 2. So these three are H1, H2, and H3 are, you can check silo 2 subgroups uh, or two silo subgroups of S4. And it's not like that I'm just able to guess it, or I did all this uh, computation, सारे subgroups calculate करें and फिर उसके बाद आया. It's not like that. They are in one correspondence with this uh, the the number of ways to write, or number of ways of writing your indexing set 1, 2, 3, 4 as the union of two sets of size 2. Okay, so they are in one correspondence to each other. If you want how this is coming, or how this correspondence I am able to write, you can see the book by Ian Herstein, and their page number something 96, 97. There a statement is there that SPK has p silo subgroup. So that proof gives you the construction of a p silo subgroup, that how the p silo subgroup exists, and from there this correspondence comes. See the number of ways in which you can write this 1, 2, 3, 4 as a union of two sets of size 2 is uh, first one is 1, 2 union 3, 4. Second is 1, 3 union 2, 4, and the fourth one is 1, 4 union 2,
2,3.
3. Right? Can you see some similarity? See first with 1, 2, 3, 4 and the first group. See, H1 is H1 stabilizes this union, or I should say, simply H1 stabilizes this, H2 stabilizes this, and H3 stabilizes this. See, I will just do it for H3, okay, because H3 is visible. Or I could just make this the size small. Now it's, we can see all three, right? So see, the elements of H1 are identity. It will definitely stabilize. 1 2 will map 1 to 2, and 3 and 4 are fixed. 3 4 will just map 3 to 4, and 1 2 are fixed. So stabilizing means this subset 1 comma 2 is either mapped to 3 4 or to itself. Okay, it won't be mapped to something else. So you can see some other elements also. It's mapping 1 to 2, 2 to 1. Here 1 is mapped to 4 and 2 is mapped to 3. So the set 1 comma 2 is mapped to 3 comma 4. Okay. Similarly, you can see the other elements of H1, and in H2 you can see it stabilizes this partition 1 comma 3 one set and the 2 comma 4 set. H3 stabilizes this 1 comma 4 and 2 comma 3. These two sets, this union is being stabilizes. 1 comma 4 can be mapped to 2 comma 3. That's a possibility, but it won't be mapped to something else or some other subset. It won't be mapped. So these three are just stabilizers of these partitions. As 1 2 3 4 can be written as the union of two sets of size 2 in these three ways. So there are three possibilities for p shallow subgroups. Okay, for each uh, decomposition you will get one. So for these three decomposition you are getting three, and what can be the maximum value n2 can take is 3. So here it's the 1 1 correspondence. Is it clear? Something different. That's
Yes,
why I
sir.
just write do this question in this way so that you learn something else. Otherwise we could do the same theoretical part that we were doing before, but I thought that it will give you something to learn, something different you will learn. Okay, so the next 7 questions, the other TA will take care of that tomorrow. You know the timing. You will get the official announcement also in the morning probably. So that's it from my side. Uh, any question if you want to ask, then you can ask. Otherwise, we will stop it here. Okay.
Thank you so much, sir.
Okay. Thank you, Shalini. Okay. There are no further questions. Then I will stop it here. Okay. Okay. See you on the next Friday. Okay.